Hello, I'm Doug Sweetser, and this is a talk I gave titled Spacetime Baseball using Quaternions. That's a picture of Minkowski, who was Einstein's math professor. Now, he was not impressed with Einstein's math skills because Einstein actually didn't go to a lot of the classes, but his friend did. And he was impressed, however, with special relativity. I mean, he says here, from now onwards, space by itself and time by itself will recede completely to become mere shadows, and only a type of the union of the two will stand independently on its own. And given this guy's a full-fledged math professor, that's really kind of radical language. So we're going to think about baseball. We got Bleacher Bob, and he's watching Newtonian baseball, where we treat time as a parameter. Now that's a good thing because we're going to take the derivative with respect to time in order to get the velocity, and the second derivative with respect to time to get the acceleration. And time here is actually kind of boring as a parameter. And in fact, there is a really small collection of people who actually think time doesn't exist. Julian Barber being the current champion of that view. Now, I think that's definitely wrong because if you really parameterize time, you're actually destroying information, specifically time itself. See, because when you're collecting the data to make your parameterized expression, you're actually writing down the time and the location. The time and the location again, the time and the location again, and then forming your function. But if you don't have the time, you don't have the parameterization of the distance. But isn't this kind of boring? Because now we take the time derivative, and that's 1, and the second time derivative, and it ends up being 0. Well, I think that's actually a way to define that you're in this classical regime. Because we can think of other people watching exactly the same baseball game. We could consider Neutrino Tony, who is sitting on top of a neutrino, which is flying by at 99.9% the speed of light, and he gets to watch relativistic baseball. Because if he was at home plate when that ball was hit, he'd be like 6 million miles away by the time it landed in right field. So he actually has to take the derivative with respect to the interval, dt d tau, and that is not boring at all. That's the gamma that shows up all over the place in special relativity. And I actually prefer this way of doing basic physics because it works both for special relativity and it works for, Bleacher Bob, because Bleacher Bob's just going to say, well, that first term is 1 and the second derivative term is 0. All right. But let's take a closer look at this ball in flight through space-time. So it covers 1 unit of space, and I'm going to claim it's 1 unit of time. And what changes, though, is our language. So space-time, well, we have to think about home plate now going to right field future. Cyclically, so home plate now again, going to right field future again. All right. And if I draw a graph of that, I've got that middle sheet of paper as labeled as now, and then the sheet in further away is the future, and the ball goes from home plate now into right field future. So what we can start to think about is reflections in a mirror, because those will be space reflections. As you can see, we go from home plate now, not only to right field future, but left field future. And that takes twice the amount of space because we've got left field and right field. It takes exactly the same amount of time because we're going from now into the future. And when we draw it in a graph, it looks like a little seagull or something like that. Now, this isn't really physical in the sense that we start with one ball and we end up with two. But we know how I did the trick. I just used a mirror. Now we can think about what a reflection around time would be. Okay, so the ball starts at home plate now, goes to right field future. Oh, and there, what's it doing going back like that? Okay, I've got cyclic boundary conditions, so it's going from right field past to home plate now to right field future. Cyclic, so right field past to home plate now to right field future. And again, this isn't so physical because balls just don't jump up from right field and make it to home plate. We are only using one unit of space there, just one thing of r, but we are using twice the amount of time because we go from the past to now to the future. But what would happen if we did both? Go ahead and try and take a guess, because I was kind of surprised by this. All right, if we do both a reflection in time and a reflection in space, what we do is we go from left field past to home plate now to right field future. So we use twice the amount of distance. We go from left field to right field. We use twice the amount of time because we go from the past to now to the future. And of course, it's not physical because the ball jumps up from left field and makes it to home plate now before continuing on the proper way to right field future. But I still find this kind of amusing because it looks like it's like continuing a path by doing both of these symmetry operations. Now we're going to ask a question about the differences between these two types of reflections that we have. And I think the most important conclusion is they look different. A mirror reflection, you can always see a pair of balls moving. And the reflection in time, you've got to remember, oh yeah, it did that, and now it's doing that in the opposite way. Because we draw in space, and yet we animate in time. Now, I think about this in terms of number theory, and I see space as having an x, a y, a z, as those being three imaginary numbers, and then time being a real number. And it turns out there's a type of number called a Quaternion, and it's on Wikipedia, and it's got its own website, quaternions.com, which I own. But the important thing to say about time's relationship to space, I think, is that space is orthogonal to time. And yet it's intimately linked mathematically because they're all part of the same number. And what is different here is that when people talk about things being orthogonal, they almost always mean the same thing. They're talking about a right angle. You can move up and down, you can move left or right, but when you move up and down, you don't do anything with the left and right. When you move left and right, you do nothing with the up and down. But there's something kind of arbitrary about, well, what's up and down versus what's left and right. Whereas here, if drawing in space is a completely separate thing from animating those sheets of paper. We could go through them super fast or super slow. And in fact, that's what the difference is between Bleacher Bob and Neutrino Tony. Neutrino Tony is running away so fast, he actually goes through them kind of slowly, the animations. And that's why he thinks it takes such a long distance and actually a pretty long time. But what can those two agree about? What can Bleacher Bob and Neutrino Tony actually agree upon? Well, in a formal sense, it's going to be the interval. Now, they've got a difference in time, a difference in x, difference in y, difference in z. And yes, we could talk about whether they're going to be differential amounts or whether they're discrete amounts, but to me, that's a technical detail. It's an important technical detail, but what we do with this is we square it. And when we do that, then we get time squared minus the distances squared. So x squared plus y squared plus z squared. And they're going to agree about those numbers. And because I'm using a quaternion, I'm also going to get these 2 dt dx, 2 dt dy, 2 dt dz, which actually doesn't have a name, which strikes me as profoundly strange because, well, it's not that complicated. So simple things by now should all have names, and yet I call it space times time. It doesn't appear to play a role in physics. And yet for these two, it could clearly play a role. They're going to agree to this Lorentz invariant interval. And those other three, the space times times value, are going to be Lorentz variant. They're going to change because those two are going at different speeds. And how much they change will dictate the difference in speed between Bleacher Bob and Neutrino Tony. So you could put it to use, although, as I say, it's not done at this time. But if you think about the numbers that go in there, okay, these dimensionless numbers for their home run are like crazy different for space and for time. Because I really want to treat it as a number, well, numbers don't have units. So I'm using what are called natural units. And that means I've got 400 feet, and that turns out to be like 400 nanoseconds. I wasn't aware of this kind of approximate conversion. It's kind of simple. But then you have to divide that by the Planck time, a super small number, which makes this a super large number. 4.7 times 10 to the 36th. And then you square it, and, well, of course, it gets bigger. 5.5 times 10 to the 73. But that 10 seconds, well, that actually gets even larger, okay? So it's like 2 times 10 to the 44th, which when you square it, wow, 4 times 10 to the 88th. And they're 15 orders of magnitude different between those numbers. And, like, nature knows how to handle this, but don't ask an experimentalist to deal with 15 orders of magnitude different between the two. So that's too bad for us, but nature apparently knows how to deal with this perfectly every single time. So I'm going to think about a different person to compare with Bleacher Bob. I'm going to talk about Radio Tower Tim, who's way up high in a radio tower. Is there anything they can agree to? Because up in that tower, gravity's going to be a little bit weaker, and so time is going to go a little faster, and the ruler that Tim has is a little bit bigger, so he'll measure distances as being a little smaller. Well, in general relativity, you go through a lot of work to start out with the Lagrange density. You derive your field equations. If things are super simple, you can get a solution to your field equations. And it turns out that the changes in time approximately cancel out the changes in distance. Now, it's not perfect, but my new proposal for how gravity works says, well, actually, you don't need Lagrangian, the field equation solutions. Instead, gravity's all about this symmetry, this cancellation of the changes in time with the changes in space being exact. And I have not fleshed it all out at the level that professionals would accept, but at least I can show you. I think this is what it's all about: is this kind of this type of symmetry of the space times time for two different observers in non-inertial observers in a gravity field. And I gave the talk wearing this very t-shirt. Okay, so why this t-shirt? Well, because it has space-time or quaternion math on it that I think covers like most of physics. If you're in the situation where you're saying, hey, time and space don't do anything with each other, they're 15 or 7 whatever orders of magnitude different from each other, well, that's classical physics. And all the lines are straight. The lines in black are always 0. and the lines in gray are always unity. Now, sometimes they're real, sometimes they're imaginary. You have to pay attention to know which one's which. Okay. And then there is fast physics, special relativity, and that's where we're thinking about a quaternion thing squared. And when you square it, the zero is actually the light cone. That's where dt squared minus dr squared equals 0. And then if it's equal to +1, well, then you get the lines that are in yellow. If it's -1, then you get the lines that are in the kind of purple section. Now, the final two graphs down there below, those are my own. And so far, I haven't convinced anybody they're of interest. But the one in green for gravity, you could see that arising two different ways. One is take that classical graph and say, hey, 1 should not cross 0. Okay, and when you do that, you get hyperboles. Or you say, hey, what if I take the fast physics guy and I rotate it by 45 degrees? Well, then instead of agreeing on a real value of +1 and a real value of -1, you say, hey, those people are agreeing to an imaginary value of I or an imaginary value of -I. It's like, oh, that's. I think that's a really nice way to connect all those graphs. But say, hold it, there's one in pink. What's on with the pink one? Oh, the pink one's the strangest one. I'm going to have even less success selling that concept than the gravity one. But you can see I was following the pattern here of saying, hey, what's a simple pattern for 0? Well, the simplest pattern of all is just a dot right dead center. And then you draw a circle around it 1 unit away. And this is when I'm always taking a conjugate of itself. So this is like dq star times dq. And I really am treating all of these planes as complex valued planes. And a circle in a complex valued plane is the symmetry group U1, which if you look it up on the internet, you'll say is the gauge symmetry of electromagnetism, Maxwell's approach to how light works. And that charge conservation is all about that symmetry. And I got it by simply drawing a circle. It's kind of simple. Now, if I think of that dr not like together as a social unit, but as three different ones, then that would have the symmetry of SU2, which is the symmetry of the strong force. No, the weak force. The weak force. And then people always say, well, what about the strong force? The strong force is SU3. It's got 3 squared minus 1, 8 independent elements that each have a normal 1. And I have not seen any connection formally between something called the Quaternion group, Q8, and the group SU3. I think they're different animals. But then I wonder whether the Quaternion group Q8 could do the most important jobs of that need to be done by SU3, essentially covering all the gluons. And I can only offer a numerology argument that maybe Quaternions are sufficient to do it. But of course, I'm pretty sure I'm never going to be able to formalize that and submit it to any journal because it's just too technically daunting for a fellow of my limited skill set. But I will say I saw it. I saw these 3 different symmetry groups when I started working with norms, and that's kind of neat because a huge question that remains to this day is why U1, SU2, and SU3. Yes, those work to explain the great collection of particles we use in the standard model, but it doesn't explain why it had to be those 3. And if you say, well, you actually need to use Quaternions, and circles and spheres and the whole thing itself might be able to put a limit on it. Who knows? We'll see. Time will tell. But it certainly has been fun to think about space-time baseball using quaternions. Thank you very much.